Every device you own, from the phone in your pocket to the world's most powerful supercomputers, operates on a binary system of ones and zeros. To find the exit to a maze, a classical computer acts like a mouse. It runs down one path, hits a wall, turns around, and tries another. It solves problems by exploring every path individually. This linear processing hits a hard mathematical wall when scientists attempt to simulate nature. To map the behavior of a single complex molecule, even a supercomputer would need billions of years to finish the calculation. This happens because the subatomic world is quantum. On this tiny scale, energy doesn't flow smoothly. It comes in discrete chunks, and subatomic particles exist as a fuzzy field of possibilities, not just rigid ones and zeros. You cannot simulate a multi-state universe using a binary machine. The sheer complexity of natural physics makes it impossible for traditional logic to keep up. In 1981, physicist Richard Feynman proposed a different path. He realized that to accurately simulate nature, science would have to build a computer out of the same quantum materials it was trying to study. This gold-tiered structure, resembling a high-tech chandelier, is the hardware required to isolate and manipulate individual subatomic particles. To understand how it works, we have to physically descend through these layers, moving from traditional engineering into the extreme environment of quantum physics. The massive top layers of this intricate chandelier structure are dedicated entirely to shielding and cooling the delicate machine. These extreme measures are necessary because of the fragility of the quantum state. This is often called the observer effect. In the quantum world, observation is a physical impact. Any stray vibration or heat hitting a particle forces its wave of possibility to collapse into a single solid state. To prevent this, engineers use a mix of helium-3 and helium-4 to sweat heat out of the system. This drops the core temperature to 0.015 Kelvin. That is colder than the vacuum of deep space. This silence is the only way to keep a quantum particle still enough to perform math. As we move into the middle wiring layers, traditional copper wires and electrical voltages disappear. Traditional electricity would generate heat and destroy the quantum state. Instead, engineers communicate with the computer using precise microwave pulses and lasers to flip the state of the particles. This unconventional method isolates the delicate core from the disruptive noise of the classical world above. At the very tip of the chandelier, the machine abandons silicon transistors for microscopic superconducting loops made of materials like niobium. These loops house the basic unit of quantum math, the qubit. Think of a bit like a coin lying on a table, heads or tails. A qubit is that same coin in a rapid, blurred spin. This is superposition. It mathematically exists as a 1, a 0, and a complex mix of both simultaneously. This is why the computer can solve the maze so quickly. It doesn't act like a mouse. It acts like a mist, flooding every pathway in the maze at the exact same time. There is a second trick called entanglement. It is a synchronized link where a change in one qubit instantly affects another, regardless of the distance between them, a strange effect that Albert Einstein famously referred to as spooky action at a distance. By combining superposition and entanglement, the machine's processing power scales exponentially, allowing it to calculate millions of possibilities in a single moment. This architecture moved from theory to reality in 2019, when Google's Sycamore processor reached a milestone known as quantum supremacy. The processor was tasked with a random circuit sampling test, which required tracking 9 quadrillion possibilities generated by 53 interacting qubits. The results were definitive. The quantum machine solved the problem in 200 seconds, a task that would have taken a classical supercomputer 10,000 years to finish. This 2019 test provided the first physical proof that a quantum machine can outperform a classical supercomputer on a defined task. Researchers are now moving towards quantum utility, applying this speed to simulate molecular interactions for life-saving tasks. The goal is to solve heavy lifting problems, from discovering new materials for carbon capture to eventually utilizing Shor's algorithm to test the limits of internet encryption. The restriction of searching for answers one by one is being replaced by the ability to calculate an entire library of possibilities at once.